Last week, I introduced various symmetry classes you can impose on the unitary time evolution operator or the Hamiltonian. And I explained that there are in total 10 classes, 2 of which are complex, 8 of which are real. And complex versus real is distinguished by whether you have an anti-unitary operator, so anti-unitary condition imposed on it. And so T and T twiddle are anti-linear, while S is linear. S is supposed to square to 1. And T squared or T twiddle square are either plus or minus 1. And you can also have S here. S either commutes with T or anti-commutes with T, and that sign is given here. So these are the choices you can take. So T commutes with Hamiltonian, T twiddle anti-commutes with Hamiltonian. And because U is exponential of IHT with an I in the exponent, the commutation relation between T and U are TU equals U inverse T, etc., etc. So these are the 10 symmetry classes. Originally started from Wigner's random matrix classes, and then lattice QCD people introduced chiral random matrices, and then Outland and Serenbauer noticed that some additional symmetry classes are possible in the context of one particle Hamiltonians for the holes and electrons in superconductor. And Outland and Serenbauer also noticed that the space of unitaries U in each of the symmetry classes have these nice form of symmetric spaces, which follow the Cartan classification, which was found in the early 20th century. So these are the Cartan names of the symmetric spaces, which are the space of the unitary operators satisfying these conditions. So Cartan classified symmetric spaces, which are subclasses of homogeneous spaces. And just as the classification of the Lie groups go, there are finite number of infinite series plus finite number of exceptionals. And the infinite series are exhausted by these 10. And these are the funny names. So the first letter D or A or C specifies the type of the group in the numerator. And the second, the Roman numeral specifies the denominator in a random order, as far as I know, originally appeared in the original paper by Cartan. So he named it in a strange order. So that's the ordering which is stuck. So that's as far as I could get last week. And I didn't have time to explain why these 8 choices are ordered in this way. Right? So what's the reasoning behind this ordering? So I'd like to start by explaining why. So the first thing I'd like to discuss is symmetry class shifting. I don't know if this is a common word. I think I've seen this somewhere, but I couldn't find it. But the idea is the following. So let's start with the easy case of complex classes. So what's the complex class A? Complex class A is just, I mean, either you have U or H and no other constraints, right? So that's fine. So this is A. And next class, I mean, here we have just two classes. So you might say that there's not much choice in ordering them, but you can still ask the following. So you have an S operator which satisfies this, and S squared is 1, right? So even in the complex class, you can ask the following. Suppose you have not only one S, but you also have S prime such that both S squared and S prime squared is +1. But, well, we've learned about Clifford algebra so much. So suppose you like Clifford algebras. And so let's say S is anti-commute. And we impose this condition for both. Right? So, I mean, we found these 10 classes by just considering various possibilities with having T or T twiddle or S. Nobody stops us to introduce more S's, right? What would happen? In this case, let's consider this product SS prime. Right? So SS prime square is SS prime, and you anti-commute it once, and this is -1, right? So, and because of these two relations, you can easily see that SS prime commutes with U, right? So you can easily, so suppose these all act on Hilbert space H, and you can decompose this H into H plus and H minus, where SS prime is plus minus I, SS prime is plus I. Then U acts within the eigenspaces of SS prime. And you can easily show that by using explicit form of S and S prime in 2 dimensions, choice of action of U within this half-dimensional subspace, and action of SU, S prime on a bigger space. So, sorry for this noise. Is in 1-to-1 correspondence. So trying to find all such U's with 2 S's is the same as just finding U on the smaller dimensional subspace. So by adding 1 S, actually you get back to the class A. So you can continue this operation indefinitely. You can try considering a possibly new symmetry class by saying that this unitary time evolution operator has this commutation relation for 3 S's, which anti-commute with each other, all square into -1. If you do that, with the first 2 S's, you do this analysis and go back to class A, and now you just have 1 S prime, S double prime. So this is A3. So in this way, by adding by imposing additional constraint by the additional existence of S, you start from A, you get A3, A, A3, A, A3, right? So in this sense, there's a nice shifting of the symmetry by the addition of additional S. So that's the complex case. We didn't have much to see here because we just had S, but things become more interesting on this side. So let's do this. So let's start with class A1, where you have just P operator, which squares to +1, and U, which is the unitary operator, satisfying that commutation relation. Right? So let's add S. What would happen? So we have T and S, and T twiddle is just defined to be TS, right? And we demand that T and S commute. Right? Then almost by definition, you get the second line. I just added S. So almost by definition, you get BDI. So this is BDI. Let's add one more S prime. So what will we find? So we consider this S operator SS prime as before. Let me change the position of the microphone. Let's consider this composite operator. So this, as I said, squares to -1, and just as before, SS prime commutes with U. Therefore, the original Hilbert space can be decomposed into H plus and H minus, where SS prime is either +1 or -1, minus I. And U act within H plus and H minus, right? However, because this is +I, this is +I or -I, T doesn't preserve H plus and H minus. T exchanges the two. And here, S and S prime are basically fermionic creation and annihilation operator. So S is also exchanges the two. I mean, explicit choice of S and S prime are, sigma matrices, Pauli sigma matrices. So they exchange S. So the combination of T and S preserves the decomposition. So, and we already introduced the name of T twiddle, right? So this is T twiddle. This is T, right? So what happens is that if you want to classify unitary operator U with two S's, together with the original time reversal symmetry T, that's equivalent to classifying just U acting on this H minus, say, with this T twiddle action defined by TS. That's exactly class D, because you just have T twiddle, no S, and T twiddle square is the T twiddle square of this previous one. So that's exactly class D. So now you have class D here. This is class D. Now you can add one additional, add S double prime, all right? So you get the idea. At this point, we already are at this stage 2, right? And you add one S. So if you add one S, depending on whether it anti-commutes or commutes with T, you go back to the original one or go to the next. But the nice choice. So you need to decide which type of S you add, right? So in that sense, suppose we are adding the same type of S's here, right? So suppose what happens if you start from T and S prime, S double prime, right? What happens is that you use two S's to go to here. So the type of S double prime you want to add here is this one. And you want to ask, what's the commutation relation of this S double prime, which you think as originally existing here, is this T twiddle, which is actually TS. So T is supposed to commute with S, but the S double prime anti-commutes with S. Therefore, this T twiddle should anti-commute with this additional S double prime, which is the negative sign here. So sorry for the confusing notation. So this just means that S at each line commutes or anti-commutes with the T or T twiddle in that line. But anyway, so that's what you find. So this is D3. Now you add fourth S. What would happen? Well, I guess I need just 3 primes. I easily get confused. So in this case, what you do is to consider this product, right? It's double prime, it's double triple prime. And you further decompose this subspace into H minus plus and H minus minus, depending on the eigenvalue of this, right? Then you just act within it. But the original T twiddle exchanges them, and the SCs also exchanges the two. So you need to define new T to be old T twiddle with this action, so which is the original T with one S here and the S double prime here. So that's the new T. So this T acts within this. And you just compute the T squared. And I'm not going into the detail, but you get this fourth class. So that's A2. So you get the idea, right? So I'm not going to work this out in detail. But you just repeat this computation. It's really a nice exercise and fun. So if you have a spare time, it's a good way to kill it. So A2 becomes C2, which becomes C, which becomes C2, C1, and A1. 1, 2, 3, 4, 5, 6, 7, 8. So that's the symmetry shifting. It's very easy. So now you understood why they are ordered in this manner. But you might still ask me, I mean, the next question is, how did I choose this to be the starting point, right? At this point, I mean, why I think this is the origin? The reason is the following. So let's say you are given a system in class I and another system class J, right? So it has a quantum mechanical Hilbert space A and H prime with U and U prime with additional T or S's depending on each class, right? And you can consider the combined quantum mechanical system. If you are given two quantum mechanical systems, you can always consider a combined system where the total Hilbert space is the tensor product, etc., etc. So what happens? Well, you can check this computation, and combined system has class I plus J mod 8. For example, there's a unique class such that, suppose you don't know what is the zero, what is supposed to be the zero of this class, right? But suppose this combination operation of the quantum mechanical systems would correspond to the addition of the mod 8 classes, right? Then the zeroth position should be such that if you multiply or tensor or add that class of system, that shouldn't change the symmetry class. There's only one such class, you know. I mean, if you have any S's, that would add S. So the old classes are out, right? The point is that this T is the most naive one, and imposing it doesn't change the symmetry. So this is the addition operation. Right. So that explains why I started this circle of classes with period 8 at this point, and similarly with this. Okay, so we now have a nice list of symmetry classes, and I explained to you why I chose this ordering. Yes. Physical example. Well, so that's a bit more complicated because here last week there was also a question in which that special dimension I'm talking about. Here I'm just considering zero-dimensional quantum mechanical class with just a right. So the addition, that's a very important. Thank you for mentioning it. That's something I should explain better. Suppose you have quantum mechanical system A acting on H, and the quantum mechanical system B acting on H prime, right? From the QM point of view, if you say you have a combined system A plus B, Hilbert space is H tensor H prime, right? So that's what you do. However, and the symmetry classes under this operation is I plus J mod A, right? However, Takasano-san asked me a different operation in the application to the classification of free fermions or topological superconductors, etc. These are one particle Hamiltonians, right? Which is supposed to be made into Fock spaces. All right. So in that case, if you have two subsystems, the combined system A plus B would have one particle Hilbert spaces, which is just a sum, right? So the total second quantized Hilbert space is constructed from one particle Hilbert space by considering all of the multi-particle states, right? So what happens is that Fock space of the direct sum of the one particle Hilbert spaces is the tensor product of the Fock space of one and Fock space of the another, right? So depending on whether you want to combine quantum systems in this way or the other, the proper operation to be used is different. So when you say you stack two Kitaev chain, what you are doing is this. So in that case, it doesn't make sense to talk about stacking systems in different symmetry classes. Rather, it's an operation within the single symmetry class. So actually, that gives an Arvidian group structure, addition structure within the symmetry class. But in addition, there's a multiplication structure among the symmetry classes. So in total, physics systems in this classification has a ring structure. Addition, direct sum operation, which is more natural from this point of view, and the tensor product operation, which would be more natural in the quantum mechanical situation. So they both become important if you want to work in a more advanced algebraic topological side of this topological superconductor business. But yeah, that's the. So thanks for asking.
Another things I thought about it is that are usually whole state to operate like you consider non-speed spaces and speed spaces and then combine them and you will get the people it is sort of 2D topology.
Right. Maybe not.
I think this is maybe not. Yeah. If so, this kind of argument is how this kind of argument works.
Right.
It's not very interesting, and it is very straightforward. I'm not sure about it.
So yeah, I mean, I think that's possible. So suppose you have suppose what one has is a free fermion system described by in some non-zero spatial dimensions, which is given by one particle Hamiltonian together with the Fock space in the second context framework. And suppose you want to add some spin degrees of freedom, right? In that case, what you are adding, like spin degrees of freedom, would be done by tensor product, right? By enlarging the one particle Hilbert space. So that would, I think, change the symmetry class by adding the symmetry class of this and the symmetry class of the finite number of degrees of freedom you are adding at each point. Yeah, so I think that's what's going on in that case.
That should be some.
Yeah. I think that might be related. Yeah. So thanks for the question. Right. So next, now that we understood very well what these symmetry classes are, let's discuss gapped Hamiltonian. So let's classify gapped Hamiltonians. As a first step into this business, let's consider 0 plus 1 dimensional systems. So it's just quantum mechanical systems. So far, we are mainly talking about U, time evolution operator. But we would like to concentrate on H. So H is the Hamiltonian. If you prefer, you can think of this as a one particle Hamiltonian of a fermionic system. And it has eigenvalues. E, and there are various negative ones and the positive ones. But you want to demand that the region around 0 is not occupied. So you think that the Fermi energy is here. So it's okay to have negative energy because they are reinterpreted as holes, hole excitations. But you want both particles, electrons and holes, electrons and positrons are both massive or gap. So you want H not to have 0 eigenvalue. So you want to have let's say we want to parameterize topologically the topological freedom in such H. How do we do that? First thing you do is the following. Generic H is very complicated, right? Because it can have various random eigenvalues E. So you have eigenvalue E, EI, EJ, J, or EK with eigenstate K, EL is eigenstate L. Let's say these are positive eigenvalues. These are negative eigenvalues. Now, it's clear that you can fix the eigenstate, but continuously change the eigenvalues so that all positive eigenvalues become +1 and all the negative eigenvalues become -1, right? So without violating the gapped condition, you continuously change, you can always continuously change such an H so that all the positive eigenvalues are +1 and all the negative eigenvalues are -1. We don't lose any topological information of the gapped Hamiltonian in this way, because most of the complications are in the choice of these eigenstates within large higher dimensional Hilbert space. So we don't lose any generality without loss of generality, without loss of topological info. We can assume eigenvalue of H is ±1. Another way to say this is H squared is 1 equivalently. So what's the space of such H? That's the question we want to ask and answer. So you might say, well, we are introducing another strange question, but you realize in a few minutes that actually we already asked this question and we have already answered it. Why would that be? Why would that be? Let's start by working out examples, and let's always start from the complex case, which is very simple. So here starts with type A, right? We want to classify this type of operator, right? Suppose you have one such operator, and we want to understand all other operator satisfying the same condition. So I mean, we always want to have one reference point. Suppose you found one, and use this operator to write this H. So as I said, H0 eigenvalue is either +1 or -1, right? So starting from big Hilbert space, you can decompose it into H plus and H minus. And dimension can be different. And any continuous change preserves the dimensions. So you at least need to fix the dimension, right? So choices of this reference point have one integer parameter, so that's inevitable. And you would like to ask, what are the other choices? So suppose this H is connected continuously to this H0. So in that case, let's say let's write H as H0 times U. H squared is 1, right? This means that H0U, H0U is 1. This means U inverse multiplying by H0. This is H0. You realize that we have seen this. If we rewrite H to be 0 to be S, this is exactly the condition of this S operator. So all you have to do, I mean, the choices in H are gap Hamiltonian, is a choice of the reference point H0, which we rename to be S, together with a unitary operator U, which satisfies this commutation relation. That's exactly the question of classification of the unitary U in the A3 class. So on this line, on this column, I had the spaces of unitaries of symmetry class A. But if you want to have the spaces of gap Hamiltonians in the symmetry class A, that result is instead the symmetric spaces for the A3 class. So this is BU times Z. You get the idea. Let me do the analysis in the A3 case, right? So here we already have S's, original S, right? And the original S is supposed to have the relation with H that they anti-commute, right? So this is the original constraint of A3. And we demand H gap. And topologically, this means that H squared is 1 by compressing the eigenvalues to either +1 or -1. So you do the same trick, fix a reference point. Then, I mean, S squared is +1. Therefore, the big H is decomposed into H plus and H minus, right? And because of this anti-commutation relation, H0 exchanges H plus and H minus. Similarly, H exchanges H plus and H minus. This means that starting from a vector in this H plus part, the image by H0 and H are related by some unitary transformation U acting within H minus. Right here, A is chosen from H plus, and the way H and H0 act are different by the action of the unitary operator U. This U acts just within H minus without any additional symmetry constraint. So in this way, you found that the topological classification of gapped Hamiltonian in class A3 is equivalent to the classification of U acting on just H, which is the original question in class A. So we just learned that the answer is just U. Get the idea? We can do the same thing in the real cases too. So it's best done by working on examples. So as always, let's start with A1. In the case of A1, you have TH with HT, right? And you pick a reference H0. So we want to classify H's such that H squared is 1. So you pick a reference point and you consider a different H. And write this as UH0. Or because of this relation, U is just HH0. So we've seen that H0U is U inverse H0, just as before. We just have additional T. So if you rewrite this as S, this is S, this is S. So this is exactly the info constraint on unitary U with P and 1S, which commute with T. So this is exactly this one, this one. So you got the BDI question. So the classification of such U is just BDI version. So this is BO times Z. So I don't have the gapped Hamiltonian column. I mean, I'm done with the complex case. So let me erase it. So this is a unitary and gapped Hamiltonian. So this is BO times Z. That's the idea. Let's work out the next case. Let's work out the next case. Suppose you want to start from BDI, in which the constraints are this one and the SH minus HS, and the TS is ST, and this is T twiddle. Right, so this is the BDI. And now we want to impose this additional constraint that H squared is 1. You pick a reference point and you want to parameterize other h's, right? So we use the same trick as we did in the complex case. So first, decompose the Hilbert space H into H plus and H minus, such that S has +1 or S has -1 eigenvalues. Then I can easily get confused. I hope I'm doing right. H, because of this anti-commutation, both H and H0 exchanges the factors. So just as I said, H and H0 are related by a unitary operator U acting within the smaller subspace. And am I getting it right? And the subspace should be just preserved by T. And T, and because T and S commute, T preserves here, right? T preserves here. Yeah, so then I got confused because the answer is supposed to be D, but I should have T twiddle, right? But I'm calling this T. But the notation doesn't mean much. What distinguishes whether you have T or T twiddle is the commutation of these anti-unitary operations with U. Okay, so in this column, T has this weird commutation with U, but T twiddle should commute with U. So we need to check whether this T commutes with this U or not. Sorry, I got confused. Here, U is H0, right? Because H by multiplying H0 from here. And both H and H0 commute with T. Therefore, TU is UT here. So more, if you want to use this table, that T should be better for T twiddle. We found the class B problem. Therefore, the gapped Hamiltonian in class BDI is just a classification of the unitary in class D, and you get the answer O. I'm not going to repeat what I said. It's very confusing at every step, but if you work it out, you always get the next plot. You just get OU, USP, BSP times Z, and SP, and SP slash U, and then finally U over O. So that's what you get. Again, this is a good exercise to kill your spare time if you have any. You can also uniformly prove it, but it's fun. But yes.
maybe I'm maybe it's about this is only about
That's right. That's right.
sometimes U and H, most of the
Right.
just you delete the
Right. 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 Yeah.
But here in this discussion, additionally talk about
Gapped Hamiltonian.
and then you also
No, in the discussion of the gapped Hamiltonian, I'm just using H, which is gapped, right? So I'm using two U's actually, so that might be a bit confusing. So far, I've always used H and U related in this way. Now I'm not using this U. I'm rather in the classification of the gapped Hamiltonian problem, I took a reference H0 and wrote other H's as UH0. I should have used different character U. So sorry about that. Right? So what happens is that then I rewrite H0 as S. So what happened was that the reference H0 becomes the additional symmetry A constraint S imposed on this unitary operator U, which connects the gapped Hamiltonian in question and the reference Hamiltonian. In that way, the question of classifying gapped Hamiltonian with a certain symmetry class became the classification of this connecting unitary with respect to a reference H0, which we reinterpret as an additional S. Therefore, the classification of the gapped Hamiltonians in class I is mathematically the same as the classification of the unitary in class I together with additional S. But I explained the symmetry shifting operation at the beginning of today's lecture. So that means classification of U at class symmetry type I plus 1. So it's a mathematical relation. Yeah. So sorry for reusing the letter U. So in this way, you always just need to pick the entry one row below. So that's very easy. So let me tell you a story. Before I start preparing this lecture series, I didn't know about this. I mean, I knew symmetry classes. I knew how to classify gapped Hamiltonians. So I always knew this. I always knew that this is part of Cartan's classification, right? But for me, BO times Z is BDI, because Cartan named BO times Z as BDI, right? But quantum matter people always called this AI. So that confused me very much. For example, in this case, O over U is D3, right? But quantum matter people always called this class D, right? So that's very confusing to me. But the naming system, so if the history of physics is different on this planet, people might have discussed this first and related this to Cartan classification, right? Then people could have named this as BDI and this as D, etc. That didn't happen. Altland, Sillenbauer somehow considered unitary operators. That already is weird. I mean, even in Altland, Sillenbauer's paper, they mostly talked about H's. But for them, it doesn't have to be gapped. So H itself didn't fit in a nice classification scheme. So they instead considered U's.
H's mean the
Yeah. So anyway, so that's very confusing. But so yeah, the naming scheme here refers to the unitaries under this image. But the gapped Hamiltonians have classifying spaces shifted by 1. So this gives the answer to the classification of gapped Hamiltonians in 0+1 dimensions, right? Right. So these are the topological spaces, and they have lots of information. But the most basic information is the connected components of them, right? So let's say two gapped Hamiltonians are, say, or declare equivalent if they can be connected continuously, right? Then classification of this equivalence class of gapped Hamiltonian or in 0+1D of type I is by definition pi 0 of this space, symmetric space written there. So pi 0 is the concept we introduced in last year in autumn. Pi 0 is just a group of connected components, right? If something consisting of one connected component, another connected component, pi 0 is just Z2, right? Things like if it's all connected, this is just M, pi 0 of M is just zero group. So I can write pi 0 of these spaces. So this is, so BU is connected, but Z is not. This just gives it Z. And the unitary groups are connected, so this is just 0. So this is Z, and similarly, this is Z. And these are known to be all connected. And this is also known to be connected. And these two are Z2. So I'm not getting into detail, but you know that space of orthogonal matrices are not connected. If you take an orthogonal matrix, you can take its determinant, and determinant is +1 or -1. So that gives Z2. Similarly, O over U is orthogonal matrices up to some unitary transformation. But this unitary action is from both sides by U and U inverse, if you remember correctly. So this unitary action doesn't change the determinant. So if you take the determinant of this O part, you still get Z2. So the reason why you have Z in these two positions are kind of obvious. And the reason why you have at least Z2 is also obvious. To say that these are all 0 requires more math, but please trust me, I mean, it's a known fact in math. So you get this. So on this side, you get Z and 0. On the other side, you get Z2, Z2, 0, Z, 0, 0, 0. So that's what you get. And that gives you the classification of equivalence class of gapped Hamiltonians in 0+1D of type I. These are, in mathematics, also known as the following. So pi 0 of this type pi space, in lack of better words, in the complex case, is denoted as k minus I of point. And pi 0 of the real type I space is known as ko minus I of point. So if you go to a library and borrow a book about K-theory, you have exactly this list of Z and 0, Z, Z to Z to 0, Z, 0, 0, 0. These are very important sequences of abelian groups. And well, this minus sign is a convention, but this is kind of not a fact. So before getting, and this underlies the K-theory classification of the topological insulator and superconductor. So let me give you a bit of an explanation. So in order to explain that, we need to give you a definition, mathematical definition of what K-theories or KO theories are. There are, and just as homology groups had various different definitions, right? In the last semester, I discussed singular homology, simplicial homology, and in the case of homology with coefficient R, we also had Doran cohomology. Everything gave, I mean, they look different. They are different as definitions, but in the end, they all became the same, right? One mathematical definition of K-theory is this. There are various versions, but one definition of K-theory of X is just the space of homotopy class of maps from this argument X to this complex type I space, where this space is just this and that. I mean, this and that. Oh, this one. That's the definition of K-theory. Similarly, KO minus X is defined as X space of homotopy classes of maps from X to a real type I space, where these are the spaces written here. If you go to the library and borrow the textbooks on K-theory and go to the KO theory section, eventually you get to the point that an alternative, usually K or KO theory is not introduced in this way. They are introduced usually in a different perspective, but eventually, once you get to the point of homotopy theoretic redefinition of KO theory, you are presented with this, where this target space are exactly this.
Sounds like exactly fine.
So here I gave the definition of K-theory for arbitrary X. And in general, homotopy class of maps from point to M is just connected component, right? Because if you have an outside point and consider a map, continuous change of this map just picks up a connected component. So it's just a point, homotopy class of maps from a point to a target space is just pi 0 of n, right? So if you are given this general definition and plug point to X, then you get this pi 0. Right. So that's the definition of K, one definition of K and KO.
Just run from 0 to
So this is take mode 2. And this is take mode 8. Even in math. Yes. Actually, Taka-san already answered it in an early part of the lecture. So if you have a gapped Hamiltonian H acting on Hilbert space H1 and gapped Hamiltonian H2 act on a Hilbert space H2, both in symmetry class type I, then you can consider the direct sum Hilbert space acted on by direct sum Hamiltonian. So this gives you an addition in the space of this classifying space. I didn't explain, but I implicitly took the infinite size limit of these matrices. So you just take, so if you are given an element here and an element there, an element here, you realize it as a block within a larger matrix. So you take 2, and that gives you an addition. That's right. Yeah, but well, yeah, either you consider finite dimensional Hilbert space, which can be made arbitrarily large later, or you can first start from infinite dimensional Hilbert space in the first place, then you can, yeah, either way. So that's that. So let me finish today's lecture by deriving the gapped Hamiltonian classification in arbitrary space-time dimension D. So it happens that we no longer need to do anything. Actually, we have answered. We already have an answer to this classification problem. So let's say H. So gapped 3 fermion 1 particle Hamiltonian in D+1 dimension of complex for real type I. So let's classify gapped 3 fermion 1 particle Hamiltonians in not in 0+1D, but D+1 dimensions of type symmetry type specified here. All right. Suddenly I have this D. So by this gapped 3 fermion 1 particle Hamiltonian, what you do is to analyze in the space of P wave number. You want to have some dispersion relation like this of complex, higher dimensional parabola. So suppose you want to have ED squared plus M squared, right? So you want to have this type of energy spectrum or dispersion relation. And we are not interested, or of course we can consider it, but so first, let's just concentrate ourselves to the property of the Hamiltonian close to a point where it can become massless or gapless. There can be more global property of the Hamiltonian related to the structure of the Brillouin zones, symmetry of it, but let's talk about it later and just consider the classification problem close to this almost massless or gapless point. In that case, as the form of the one particle Hamiltonian, you suppose this linear dependence of the Hamiltonian and this complex or real type I refers to the symmetry type of this constant part H0. So if D is 0, this is just a classification problem we just discussed in dimension 0 plus 1. Now we are adding Dirac type Hamiltonian. So alpha I squared plus 2 plus 1. And alpha I anti-commutes with H0. And alpha I needs to anti-commute. So that's the standard Dirac Hamiltonian. So I mean, in 3 dimensions, you just do in the complex case. So that's just that. But one important point is that so the classification of H0, such gapped Hamiltonian in this form is just the classification of gapped H0 of symmetry type I, but with D additional alphas. And mathematically, these behave exactly like almost like S's we've been talking about. That's another reason why I talked about this symmetry shifting operation in the first part of the lecture. So that symmetry shifting was very useful in the classification of gapped Hamiltonian, supposing you know the classification of unitaries, but it also useful in studying the classification of H0 in higher dimensions. But there's one important point is that if you in complex case, it's fine. That's the end of the story. But in the real case, time reversal invariance T sends pi to minus pi because time reversal invariance changed the motion of the particles. So this means that in order to compensate, alpha I should anti-commute with T, unfortunately. So far, we are in the symmetry shifting analysis, we assumed all of the S's to commute with T, but here we need to add alphas which anti-commute with T. So you need to redo the analysis in some way or other. So, but the point is that if you add S which commutes with T, you go down the list. But if you add alphas which anti-commutes with T, you go up the list. So well, you can check it. I don't know how to explain this better. But the point is that this, because thanks to this symmetry shifting argument, is the same as 0 plus 1D with type I minus D. Therefore, the result of the classification is either K D minus I or K or D minus I or point. So this is the final classification result for the gapped Hamiltonian of the free fermions with the symmetry type I in dimension D plus 1. So yeah, it's a very good place to stop by writing down this periodic table. So in the complex case, it's not very difficult. So dimension D can be 0 or 1, and symmetry type I can be just 0 and 1. So this is just A and A3, if I remember correctly. And this was Z0, and you need to shift them. This is Z. So that's just that. I need to split this into 8. I'm getting confused. This might be a bit too small. Let's try something bigger. Let's try something bigger. Well, I could have written this on the blackboard from the start, but together with that table I needed to keep during the lecture, that would have filled almost half of 2/3 of the blackboard. So that was, oh God. Right. The type, so dimension mod 8 and type I and 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. And I easily get confused in which direction I need to shift. So this is Z, Z2, 0, 0, Z, 0, 0, 0, right? And you need D. What you need is KO D minus I, right? So when D is I, you just get Z. So this means that I need to shift it. This is Z. So this is Z2, Z2, 0, Z, 0, 0, 0, Z2, 0, Z, 0, 0, Z, Z, 0, Z, 0, Z, Z, 0, Z, 0, 0, 0, 0 and 5. Z, 0, 0, 0, and finally Z, Z. Good. So this is a famous periodic table of topological insulator and topological superconductor. And because I spent almost 2 or 3 weeks in the preparation of what is a fermion, or what is a Clifford algebra, what is K-theory, and what are symmetric spaces. I mean, the final derivation of this periodic table was immediate, right? We didn't do anything because we already prepared everything. So before getting into this general discussion, we consider a 2 plus 1D bulk, right? 2 plus 1D bulk. And 1 plus 1D boundary system. Boundary system in a relativistic setting. Right? And in the relativistic setting, we consider three cases: spin case and spin minus and spin plus. So spin symmetry is just a standard Lorentz group. And spin plus, spin minus and spin plus corresponds to having parity transformation and time reversal transformation, but such that t squared is plus 1 and t squared is minus 1 to the f. So these are the three cases. And we analyzed the Hamiltonian, space of gapped Hamiltonian in the bulk, and the question of having a massless or gapless pinned modes on the boundary. And we learned that the classification here was Z, and this is Z2 and 0. So we worked this out very explicitly. So we already seen these three choices, and as I discussed, if I remember correctly, we already said that this class D or class type 2, this was relativistic spin symmetry, and this has spin plus, and this is spin minus. So that should correspond to these three. And this is the spin case, and this is spin minus, spin plus. So our long endeavor in developing the general framework to classify free fermionic phases nicely reproduced this classification result 0Z2, 0Z2 as part of it. So that's very nice. So that's the classification of the topological superconductor topological insulator when the system is free. Right. So as I need to leave early, I really think it's a good place to stop. So next week, I'm going to our topic shifts to the classification of interacting interacting fermionic phases. And we'll discuss that our main example, even the main example in the Honda literature is the fate of these three Z classes. Pin minus in 1 plus 1D, spin in 2 plus 1D, and pin plus in 3 plus 1D. If you add interaction, it is known that this Z remains Z, but this Z is known to reduce to Z8, and this Z is known to reduce to Z16. This part, actually, we already explained. So this is the result of Kitaev and Fidokovsky. So we are using Kitaev-Fidokovsky result in two ways. So in Kitaev-Fidokovsky, what was found was that if you have 8 fermions, real fermions acting on a quantum mechanical space, you can gap it, right? If you take that physics fact as a mathematical statement about Clifford algebras, that explains periodicity by 8 of these 8 by 8 matrix. But you can just use that quantum mechanical fact about 8 fermions in this way. So if you have p minus, and when d equals 1 plus 1 in the bulk, the boundary is 0 plus 1d, right? And consider this p minus case. So in the free classification, you have z. That corresponds to the Kitaev chain with time reversal. And Kitaev chain with time reversal is basically just a Ising chain in fermionic formulation. So it has boundary modes. Boundary Majorana fermion zero mode. And this Z counts this boundary fermion zero modes. And considering just free Hamiltonian means that you only allow quadratic fermion Hamiltonian. So that explains this Z classification. But if you allow interactions, this means that you allow interactions, not just keeping the states in the one particle subspace. You allow multi-particle operators. And we have seen in our discussion that if you allow quadratic operators, then if you have 8 Majorana Weil fermions on the boundary, you can gap it. So that explains why 8 Majorana fermions can be gapped even on the boundary. So that means that within the bulk, you can continuously change 8 gapped free fermions in a non-trivial class A, 8 in Z, continuously to trivial class. So that we already saw, but we'd like to see them from a more generic perspective. So thank you very much for your attention. So this is the end of the lecture today. So see you next week. Thank you. Yeah, if you have questions, I have 5 minutes or something. Yeah. Yes. Mm-hmm. Uh-huh. Well, the point of view I took last week was to classify possible choices of symmetries you can impose on any quantum mechanical system with time reversal symmetry or order 2 symmetry S, without specifying whether it's fermionic or not. So that was the original point of view of Wigner and Altland-Zillenbauer. So Altland-Zillenbauer used that as a guiding principle in the study of generic Hamiltonian acting on the one particle subspace of a superconductor. Yeah. That's right. That's right. Yeah. Yes. Right.
It seems like just a rewriting idea to take. I was not clear about the role of cases. If we know what is the I0 of subspace group, and then we can say, yeah, we can write down all the table, and then maybe it can be say we. Yeah, whenever in that sense we can replace the theory instead of that we can say just the form. I don't know the meaning of the how to this three kind of classification is done by case theory. So I don't know the.
Well, I mean, the physics output of our analysis is that gapped Hamiltonians in various dimensions are parameterized by these spaces. So this is a fact even before taking pi 0. So you don't have to use K theory. This is very important result. So the classification of D plus one dimensional free fermionic phase up to homotopy equivalence is given by this, where you use B minus I.
My point is that it sounds like you just read the people algebra, and is there any new machinery come from a theory or something like a theory give more simplified discussion, or I don't know. So
that's a very good question. The important point is that K theory is Clifford algebra. K theory is these symmetric spaces. So if we live in a different planet with a different history of science and mathematics, people could have discovered these nice sequence of spaces first and called the resulting mathematical structure free fermionic something, right? In that hypothetical planet, people would not have called this K theory. Rather, it's that classification of free fermionic phases are also useful for various work in mathematics. It's just that K theory was found by mathematicians a couple of decades ago, but the structure you find is exactly the same. So it's not that K theory or KO theory gives you additional perspectives to the analysis of the free fermionic phases. It's just that they are literally the same. Yeah. So if you go to a library and borrow a book on K theory, exactly the same discussion of Clifford algebras and adding of this shifting symmetry classes appear there. Yeah. So so it's not that K theory or KO theory gives additional information. It's just that the development of K theory and KO theory is equivalent to the analysis or development of the classification of the free fermionic phases. Thank you for the question. Maybe one more question. Is that fine? Oh, okay, let's end the recording.